Hi, I'm Eva Murphy from Electronic Engineering at IT Sligo, and this is my Leaving Cert Maths Grinds channel. I'll regularly add new videos for both higher and ordinary level maths, so make sure you subscribe below and click the bell icon to be notified of new videos. The third formal theorem on your course is Theorem 13. Again, I'm using Project Maths just like I did for 11 and 12. This theorem states that if two triangles, ABC and DEF are similar, then their sides are proportional in order. Okay. Similar triangles, okay? Similar triangles, so you have congruent triangles and similar triangles. Congruent triangles, we would have used this in Theorem 11, that's when all angles and all sides are equal. Similar triangles, their angles are equal, but not their sides. So in other words, one triangle is like an enlargement of another. So their angles are the exact same, but their sides have got bigger. Or of course smaller. This could be the original and this could be a shrinked down version of it. Okay, but in all cases, for similar triangles, their angles are the exact same. So this one line that's on this angle here and one line on this angle here means that angle B equals angle E. The two lines here and the two lines here means angle A equals angle D, and then there's three lines here and three here, angle C equals angle F. Okay, and of course for similar triangles you just need to show that two of the angles equal each other, because then naturally the third one will, because of all angles in a triangle being equal to 180. Okay, so that's what similar triangles mean. So what this theorem is stating that if you know that two triangles are similar, then it wants to show that their sides are proportional to each other. So when you talk about sides being proportional to another, so we'll say this was the original one and I enlarged it to give me ABC. I would have to, for example, increase this by a factor of 2. Okay, and then I would get perhaps the larger one. So that's what in proportion means. You increase everything by a factor of 2. Adding a number to each of the sides, so we'd say this was 3 centimeters, adding 2, for example, 2 centimeters to each side doesn't work because that may not be in proportion. So in other words, if you had a really small side, adding 2 to that side has a much bigger impact than adding 2 to that side. So you're not keeping your sides in proportion when you do something like that. It's a bit like percentages. So you must do a multiply factor, or what's called a scale factor. So multiplying by a certain amount keeps everything in proportion. Okay, or dividing, which is what the proof here is looking at ratios of sides. Right, so let's get on with the proof then. So what are we given in this one? So just like any other proof, these are your headings. We are given two similar triangles, ABC, DEF. Okay, we're to prove that the sides are in proportion. So in other words, the sides that correspond to each other, you have to have your triangles lined up. And by that I mean, do you see the way these are the angles that's equal to each other? They're on top. These are the angles that are equal to each other, they're to the left, and then these ones are to the right. So the two triangles line up with each other. And when that's the case, then you can say things like the side AB over the side DE equals the side BC over the side EF. Okay, so it's missing little equals to sign here, which is equal to the side AC over DF. Okay, so that's the theorem that you're trying to prove. The sides are in proportion. AB corresponds to DE, AC corresponds to DF, BC corresponds to EF. It is also the exact same thing to say that DE over AB is equal to DF over AC, which is equal to EF over BC. In other words, I could start with the small triangle and go DE over AB, which is that one, equals DF over AC, which is equal to EF over BC. Both of these are the exact same thing, okay? But what is really important is that if you start with the small triangle here on the top, then in the other two pieces, you must have the small triangle on the top. Or like you did in this one, you put the large triangle on the top, then the large triangle has to be on the top for them all. And that's the only way that the theorem works. Okay, so which one's on the top and the bottom doesn't matter as long as there's consistency with what you do. So that's what we're trying to prove, that the sides are in proportion. So I'm not saying that they're equal, I'm saying that there's a scale factor here. So AB over DF is in the same proportion or the same scale as BC over EF, which is the same as AC over DF, okay? Okay. So, do we need a construction on this? Yes, we do. We superimpose the small triangle onto the big one. That's more or less what we're doing. What do I mean by that? Well, you pick a point G on AB and the distance from A to G has to match DE. Okay, AG must be the same length as DE. And in the same way, you pick a point H on this side AC so that the distance AH completely matches DF. And if you do that, then when you join G to H, like I've done there, that's going to be the exact same distance as EF. Okay, so in other words, I have now an exact replica of this triangle sitting here on top of ABC. Okay, and I can do that because remember D and A were the same angle. Okay, which means these lines are coming out at the same angle as those two, so I can create this replica sitting on top. So pick a point G on the line segment AB such that AG is equal to DE. Pick a point H on the line AC so that AH equals DF. And you can see the ticks again. The ticks are trying to show you what's equal. 2 ticks there matches 2 ticks there. That's how I know those sides are equal. 3 ticks here matches 3 ticks here. And of course I can put a single tick there if I wish to show that they're equal. You will see that construction line on some of the proofs in different books. Okay, and the proof then. Okay, so the proof. The statement triangle AGH is congruent to the triangle DEF through SAS. And we would have done congruent triangles again as in Theorem 11. So triangle AGH is congruent, that's what those three lines mean, to triangle DEF through side, angle, side. Okay, what does that mean? Well, congruent, like I said, exact same angles, exact same sides. And a triangle has 6 pieces of information. It has 3 angles and it has 3 lengths of sides. So there's 6 pieces of information about any triangle. You just need 3 pieces of information to show triangles are congruent. And if 3 pieces are the same, then all 6 will be the same. Okay, so what we're doing here is we're stating, well, that side we've already said is the same as that because we deliberately drew it like that. This side AH is equal to DF. Of course it is, we drew it like that. And then we're saying angle A is equal to angle D. And this was given. This was given because they told us the triangles were similar. Okay, so that's where they're getting the side. That's the side AG and DE. The angle is angle A and D are equal, and then the other side AH and DF are equal. And if anybody needs me to do any more videos on congruent triangles or doing out more of them, just let me know on YouTube and we can do some more. Okay, so they are congruent, and you can write it in English or you can write it as such in maths language. But that's your first statement. You're saying this triangle is congruent to this triangle. Okay, next we are saying that this angle here corresponds to this angle here. It's equal. Okay, so that's what we had in the last slide. Angle AGH, which is this one, equals the angle ABC. Okay, I would like to see why here. These are corresponding angles. Okay, and we did a little bit of these types of angles too in Theorem 11. Corresponding angles, you're always looking for an F. Okay, where the arms of the F's are parallel lines. Okay, that's your corresponding angles. They're under the arms of the F as such. And of course I can have backward versions of this. There's your corresponding angles again. And have I got all four there? I think I do. Yeah, they're all just mirror images of each other. So you can see it's this fourth one that I've drawn that I've here. If I can just mark in the F for you, just go up to a thicker line. And you see the two parallel lines here. Okay, that's my F. And under the arms of your F are your corresponding angles. Okay, so that's why these two here are equal. Okay, you should have this written to the right. Why are they equal? Okay, they're corresponding angles. Or the other way you can say is similar triangles. I probably should say that as well, okay? It's too thick. Similar triangles. This is probably what this diagram is showing because they've brought in angle E. Angle E is equal to angle G, but that angle corresponds to this angle B down here, okay? Because remember, that's what they told us in similar triangles. Okay, so angle E is equal to angle B because of similar triangles, and then because of how we drew it, angle B is also equal to angle G. Okay, so they're equal because of similar triangles. They're also corresponding angles, and if they're corresponding angles, that can only happen if this line GH is parallel to BC. Okay, because corresponding angles can only occur with parallel lines. Okay, so you have now established that that line GH is parallel to BC. Okay, and when you have that parallel line parallel to the bottom, that should look like Theorem 12 to you now. And if you remember Theorem 12, it says that they cut the lines in the same ratio, so that AG over AB would be the same as AH over AC. That's what Theorem 12 told us. If it cuts one side in the ratio, then it cuts the other side in the same ratio. And that's why they have that statement there with the reason why after it, Theorem 12. AG over AB is equal to AH over AC. Okay, so then what do they say? They say then you could write it as, instead of AG, you can say DE, because remember we designed them with their constructions that they're the same. So you replace AG with DE. Now from that, that's the same. And then instead of AH on this side, you replace it with DF. Because again, that was the construction you did and you made them be the same. Okay, and that's what that note there means. And then finally, you can flip them upside down. Remember I said it doesn't matter which triangle you start with, so flip that upside down so that it becomes AB over DE is equal to, flip this one upside down, AC over DF. Okay, AB over DE is equal to AC over DF, which is equal to then BC over EF. And it's perfectly fine to say similarly on that one because it's using the same principles that side also comes into it. Okay, and that then is the proof of Theorem 13. If you've enjoyed this video, then why not join us in IT Sligo and use maths in practice. In conjunction with industry, we've designed an exciting new program in electronics and self-driving technologies, which uses cutting-edge techniques such as artificial intelligence, computer vision, and virtual and augmented reality. You'll need a H5 in maths to qualify. Check out the link below.